So this is the fourth session on the stereochemistry topic. So here we'll solve some problem based on the topic covered by the professor on the in the week 4. So first I will introduce myself. This is Vijay Rahane. I'm a research scholar in the IIT Delhi and the University of Queensland, Australia. So basically, I'm working on the organic optoelectronics material synthesis, design synthesis, and its application in the various optoelectronics devices. So I'm currently working on the uh, application of the synthesized material for the laser. And this course is covered by the Professor Amit Basak. He is from IIT Kharagpur. So we'll see the most of the problems. I think someone is unmuted. Can you please let me? So we'll cover most of the problem today on the topic based on the prochirality, pro R, pro S designation related problems, and some confirmation of acyclic systems like cyclopropane, cyclobutane, this one, and also the Newman and the uh, gauge projection and their stabilities, the problem based on the stability of the different conformation of the alkanes. So this is the some problem we have left or in the we have not solved. Let me just hide this one. Oh, all right, not perfect. I'll put it on the presentation mode. So these are some problems that we have forgot to solve in the last video. So I will cover this problem first. Uh, the methyl group in the following molecules are, we just need to identify whether it is enantiotopic, diastereotopic, or heterotopic or homotopic. So this is the just simple problem. Probably no need to spend time on this. I will just, these are the two methyl groups, right? So I will just quickly show the what is the correct answer of this. So these two are the methyl group that we need to distinguish from each other. So if you see this molecule perfectly, see this molecule, we can draw a C2 axis from here, right? So if you draw the C2 axis from this plane, this one, the C2 axis, uh, and rotate this molecule by across the 180-degree. So we'll get the identical molecule, identical structure, you can say. So basically in this molecule, the C2 axis is present. So we need to identify whether the molecule is anisotropic, diastereotopic, or homotopic. These methyl groups are. So the correct option for this, if anyone want to just paste in the comment, they are feel free to just comment it. So we can just, it's like a interactive session. You can also, it will also involve in the solving the problems. So we got one answer. So it's homotopic. All right. So one option is the homotopic. So what anyone want to identify whether it's homotopic or heterotopic, some. All right, if there is no any option, then I will just tell you. Yes, the option is correct. It is homotopic because it has the C2 axis, right? So the C2 axis is there. It means these are the, if you rotate the molecule by 180 degree, we will get the structure in which this methyl group goes to the position of the second methyl group, and the overall configuration and the overall molecule will be the identical after C2 rotation. So this methyl group is homotopic. So here just I have pasted here. I will share this slide with you, so you can also have a look on this. What is homotopic? What is enantiopic? And this homotopic, enantiopic, these are mainly important in the field of spectroscopy. So if someone here from the masters, so they will probably know the importance of this homotopic, enantiopic protons or the distereotopic. So they give the homotopic proton give the same signal, but the enantiopic protons, they give the different proton signal in the proton NMR spectrum. And also the distereotopic proton also give the different signal. So you can have a look for this. The next question is the stereochemical description of the alpha phase of the pro-stereogenic center of C1 and C4. So alpha phase is alpha and beta, we know, right? So if the structure, if you have a structure, so let's say if you have a structure, these upward directing groups they called as beta, right? And downward directing group they called alpha. So just always keep in mind. So most of the people uh, to make mistake here, they consider as the upper phase as the alpha and lower phase as a beta, but this is not the case in terms of the stereochemistry. The upper one is called as the beta, and the lower one is called as the alpha. So the atoms which are directed downward, let's say here one atom is attached and directed downward from the plane of this plane of the ring. Let's say here is hydrogen. So this hydrogen is the alpha hydrogen, and if the hydrogen directed upside here, so this hydrogen is the beta hydrogen. So always keep in mind. So we need to identify the stereochemical description of alpha phase. The alpha phase means the lower side. So we just need to give the numbering, and from we have to look the molecule from the downside. So if you see this structure of this molecule, just keep in this way. So I'll give just numbering for this first one, C1 and C4. So here is the numbering 1, here is the 2, and that side is 3, right? So if you look from the, so if you, let's say, if you look from the upper side first, 1, 2, 3, right? It's anti-clockwise, right? So anti-clockwise means psi phase. But this one, when if you look from the beta phase, right? Since we are looking from the upper side, so this will 1, 2, 3, it will looks like the, if you look from the upper side, that is from beta phase, 1, 2, 3, this will be the psi, right? Psi from beta phase. So obviously the from alpha phase, it is Re. Similarly for the second, this is for C4, C1. Similarly for the C4, I'll just rub this for understanding. So if you give the numbering for the backside phase, so C4, this is the 1, this one is the 2, and this one is the 3. So 1, 2, 3, right? It is Re from the alpha, so from beta phase. From beta phase, if you look from the beta phase, then what it will be? 1, 2, 3, it's Re, right? But from alpha phase, If you're not able to imagine from the bottom side, just uh, uh, try to visualize from upper side and just reverse the configuration whatever we got. So in this structure, it's difficult to look from the molecule from the downside. So better you can. Oh, I think video is paused. So you can look from the backside. So you can look from the upper side, that is from beta phase, and just do the invert. So if I look from the upper side, it looks like a rephase, and just from alpha side, it will be definitely the psi phase. So always you can try your method, but I like to visualize from upper side, and whatever they ask alpha phase, so I just did the reverse of this, whatever we get the configuration. So this is just a simple example. We just need to identify the pro-stereogenic center, whether it is alpha from alpha side, or we have to see whether it is the phase is psi phase or the rephase. So this is the problem. Here also some explanation they have given. So yes, here you can see. Here option B is the correct option for automation. So at the C4 it is re, and at C4 it is psi. C1 it is re, and C4 it is psi phase psi. So this is the B option is the correct option. The next question is the pro R hydrogen in the following molecules are pro R hydrogen in the following molecules. We just need to identify pro R. What is meant by pro R? So here it is like if you replace one hydrogen, ignore the spelling. So if you replace, let's say in this center, if you see from this center, uh, for this center, if you see, oh sorry. So if you replace from this center, if you replace the hydrogen by deuterium, let's say, so what will be the configuration now for this center? So 1, 2, and 3. 1, 2, 3. It is S. Hydrogen is backside. 4 priority group will be the backside, right? I'll just give the numbering for your understanding. 1, 2, 3. So 1, 2, 3. It's a anti-clockwise, right? So anti-clockwise means it's S configuration. So if you replace this hydrogen by deuterium, we'll get the center with the S configuration. So we need center with R configuration. So obviously the HB is the pro R, and HA by default it is pro S. So here HB is pro R. All right, we'll see for the next center now. So for the next center, I will just give the numbering. Let's say it's 1, and this one is the 2. And if I just give the numbering, I will just replace this alpha C by deuterium, sorry, hydrogen C hydrogen by the deuterium, let's say, so, and try to get the configuration for this chiral center. So what is the configuration now? See, the hydrogen is upper side, so we need to invert the configuration, right? Just keep in mind 1, 2, 3. So here it's R, that is clockwise, which changes to S, right? So if you replace this hydrogen HC, we'll get the compound with the S configuration. So we need the center with the S configuration, but we need R, right, for pro R. So this is definitely the pro S, and HD is pro R. Sorry. right? So HD is Pro R. So here in this one, which option is the correct one? HB and HD. So the option C is the correct option. These hydrogens are the Pro R hydrogens. So inward different question may also come. What is the Pro S? So you can identify on this way. So anyone have doubt, please interrupt me in between. Uh, or can we move further? All right, if you don't have any doubt, I'll just move further because we have to solve today a lot of questions. So here, the two N-cycle methyl groups of the molecules are whether they are enantiotopic, diastereotopic, homotopic, or constitutionally heterotopic. So just just previous 2-3 question back, we have solved such questions, right? Only difference here is the here you can see here this is a chiral center. So always keep in mind it's already have one chiral center. So and from the other side there is no such chiral center, right? And here is the ethyl, and here is the propyl chain, right? So these methyls are definitely not enantiotopic. So we neglect this option. If you see this molecule, this is not symmetrical, and this methyl definitely they are not sorry, they are not homotopic, right? For homotopic, they should be similar, and some kind of C2 axis of symmetry should be there. So this is definitely not homotopic. Now the option between the diastereotopic and the constitutionally heterotopic. So constitutionally heterotopic means I think this comes in the different isomer. So the best option is the diastereotopic one. So here is the option answer. The two methyl groups are not related by any symmetry. Therefore they are diastereotopic. Constitutionally different, the option is not for the same molecule, right? So if there are two different molecule A and B, then it come in the picture. They are constitutionally heterotopic or something. So the option B is the correct option here. Any doubt here? So before going to the actual problems from the this week 4, so anyone have any doubt uh, from the whatever the portion you have covered? Just ask me. Someone have asked the question doubt on the. I'll just insert one slide. So I'll just ask one question someone asked in the doubt session. Sorry, discussion. See, this is the molecule, and uh, in this molecule, he or she want to ask regarding. So this molecule, if you see, this molecule has the plane of symmetry, and if you consider the configuration of this each and every center, so this is C2, C3, C4. So what is configuration here now? 1, 2, 3. It's R changed to S. For this one, we need to find out, right? And for this one, it's 1, 2, 3. It's yes. changes to R. So this molecule, if you see this molecule, this has the plane of symmetry, and this S and this R, these two groups are different here. So what is composition of the in-between carbon atom? So the C3 carbon atom. So the composition of C3 carbon atom, I will just draw. I will just give the priority. The OH will get the first priority. The R group which get the second, and this upper one get the third priority, and the hydrogen obviously get the fourth priority. So the compression for this C3 is 1, 2, 3. So it's R, which changes to S. So the configuration for this C3 center is S configuration. And the next part is when such scenarios happen, like this. So if you see what is the compression for the first center now, 1, 2, 3, it's R changes to S. So, and 1, 2, 3, it's 1, 2, 3. R changes to S. So what is the compression for this C3? So they want to ask what is compression of in this structure B. If anyone have the answer, please can you comment, or you can unmute and you can discuss. So later I will solve the, I will let you know what is the correct option. So what is configuration for this one? All right, we'll get the answer from Soumya. It is for city, for the center. She said it is a chiral one. Does anyone want to give the answer? All right. The correct option, correct answer is right. Soumya is right. So this center is a chiral one. So this C3 carbon, a chiral carbon atom. So why it is a chiral carbon atom? If you see the group, let's say I will draw here. Let's say OH get the first priority, and hydrogen get the fourth priority, right? So, but if you look at this, both upper and lower part, the square and the, let's say it's semicircle or whatever it is. So this upper part and the lower part, so they are the identical groups. They are not different from each other. If you see in the case of structure one has the S configuration and one has the R configuration. That's why the groups are the different. But here in this case, they both have the same configuration. So both get the same priority, right? Or we can't, this molecule is not chiral molecule, chiral center, because of both have the same chiral, both have the same configuration. So this upper group has also has the S configuration, this also has the S configuration. So this both are identical. So that's why this center is a chiral center. So this was the answer for that question. So if anyone have any other question, just let me know. You can unmute or you can comment in the chat box. If you don't have any question, we'll move for next questions. So here one question is, among the possible staggered conformation of the erythro 3 amino pentene to OL, consider C2 and C3 rotation. Which of the following statement is correct? So they have given a molecule, and this is the IUPAC name of the molecule they have given. and which of the following statement is correct. And we need to consider the staggered conformation of this molecule. So first of all, we need to draw the staggered conformation of this molecule. So we'll draw a staggered conformation. So I will just draw a molecule in this format. Oh, sorry. So this is the CH3. This is the OH. And this is the hydrogen. And this is the C2H5. NH2H. Can you tell me whether I have written it correctly or not? If anyone have the anyone have I will directly go to the next I will go to the one by one options. So the first option is the two staggered conformation are possible for the given erythro aminophenol. Two staggers are possible. Next one is all the staggered conformations suffer from alkyl alkyl gauge interaction. So what are the staggered conformation possible for this molecule? They suffer from alkyl alkyl gauge interaction. Say a third option is intramolecular hydrogen bonding between NH2 and OH group is possible in the two staggered conformation. And last option is intramolecular hydrogen bonding between OH and NH2 groups is present in all the possible staggered conformation. So we need to draw all possible staggered conformation first. So I will just draw directly the staggered conformation for these molecules. So this is the, let's say, 1, 2, the C2 carbon atom. Let's say I will draw the methyl group up as it is, CH3. Oh, sorry, CH3. And one is the hydroxy group, and one is the hydrogen atom. And this lower one, so I'll just make some sense. This is not required at all. So the lower one, which has the hydrogen and NH2 and CH2. So if you draw the structure, we need to fold it, right? This fold from this center. So this one goes to C2H5 and it will go the opposite direction, and the NH2. Right, I will just check the compression of both are whether I have written correctly or not. So what is compression for this center? 1, 2, 3. This is S changes to R. And what is compression for this? 1, 2, 3. S changes to R. Right. So both center have the R compression. So it should be here also. In this one. Oh, sorry. I have converted this hydroxy, right? 1, 2, and 3. All right. R. What about the backside carbon atom? All right. This is the structure for this molecule in the staggered form. And what are the different staggered conformation possible? If I rotate this molecule by 120 degree, right? So what is this possible structure? So I will rotate backside carbon atom, and this is the, oh sorry, yeah, this is the hydrogen and this hydroxy group. What about backside? I have rotated the molecule by 120, sorry, 120 degree, either clockwise or anti-clockwise. So let's say I have rotated this molecule CH2. So this CH2, I rotate this at the position of here. So this will go there and C2H5. Here will be the NH2 and here will be the hydrogen. So this is one form possible. But another one, if I rotate it anti-clockwise, sorry, clockwise. So what is another form? Just discard this. Now here I have rotated anti-clockwise. Now I will rotate it clockwise. So C2H5. Here is the hydrogen, and here is the NH2, right? So these three forms are possible, right? Only three staggered conformation for staggered form for one conformation is always possible, right? Across the two carbon atom. So here is the for this one and this one, two carbon atoms are present. So we have rotated this carbon bond to get all possible staggered conformation. So these are the three staggered conformation are possible, and we have to find out which is the correct in this one. So the two staggered conformation are possible. This is the wrong option, obviously, because always there are three staggered conformation possible for rotation across the bond, right? Because there are 1, 2, 3 positions are available, so we can move the molecule from all possible way. So this CH2, let's focus on this CH2 C2H5 group. Now here it's the left hand side, here is the bottom, and here it is right hand side. So these three positions are possible. So these two option is obviously the incorrect option. Two staggered conformation are possible for the given enantiomer. This is incorrect one, because there should be three. All staggered conformations suffer from alkyl-alkyl Gauge interaction. So alkyl-alkyl Gauge interaction means here which are the alkyl groups? This C2H5 and this CH3. So we need to look at so we need to look at this CH3 and C2H5. So if which are the possible structure in which these are the gauges to each other. So in this three form, you can see in this form there is no gauge interaction between this CH3 and C2H5. They are anti to each other. In this one, yes, there is one gauge interaction. Here, in the second, I will just label it as, let's say it's A, this is B, and this is C. So in the C structure is also present gauge interaction. So 1 and 2. Two structure are possible with the alkyl-alkyl gauge interaction. They have mentioned all. So this is incorrect. So there should be a 2. Sorry. Two staggered conformations are possible for alkyl-alkyl. They have mentioned all. So this is incorrect option. The third one is the intramolecular hydrogen bond between NH2 and OH group is possible in two staggered conformation. What they have mentioned, intramolecular. Intramolecular means within a molecule. So, and intermolecular means within two different molecules. So it is now they have mentioned there should be a can you confirm the camera is on or not? So right. So in this one, intramolecular means within a molecule, and intermolecular means between two different molecules. So we need to find out within a molecule. So this is the three different staggered forms are possible. And intermolecular, when the intermolecular is possible, when they are gauges to each other, right? If they are anti, then there is no possible. So we'll see in the structure B. In the structure B, we can see the OH group this hydroxy group and NH2 group, they are opposite from each other direct by 180 degrees. So there is definitely not intramolecular interaction is possible from in this structure. If you see the structure A, in this hydroxy group, and this NH2 group. So this NH2 group, they are Gauss to each other. So there is a special intramolecular interaction is possible in this A structure. And if you see if you look at the C structure, so there is also this NH2 and hydroxy group, they are away from each other by they are close to each other. So definitely there is also possibility of intramolecular hydrogen bonding. So in structure A and structure C, there is possibility of hydrogen bonding. So intramolecular hydrogen bonding between NH2 and OH group is possible in two structure. This is correct one. So in structure A and in structure C, the intramolecular interaction hydrogen bonding is possible. So this is one correct option. And the D option is the intramolecular hydrogen bonding between NH2 and OH group is present in all possible staggered conformation. They have mentioned all possible, but if you see this staggered conformation, the hydroxy group and NH2 group, they are away from each other, right? By 180 degrees. So there is obviously no intermolecular interaction present. If they mention intermolecular, then intermolecular interaction by default is possible because the two molecules, they can come to close each other by any direction. But here intramolecular they have mentioned. So if you see the intramolecular, they are not able to, this hydrogen and this nitrogen, they are far away from each other. So there is no possibility of intramolecular interaction between this. So this D option is incorrect option. So most correct option is the C option is the correct option. So anyone have doubt in this one? All right, we'll go for the next question. Right here, you can see yeah. And I have just kept here some diagrams. So just for understanding for our next problems. See, this is the potential energy diagram for the N-butane. I'll draw the structure of N-butane here in the form of, see, N-butane which contain one CH3 group, and let's say I will draw the anti-structure, hydrogen. So this is the anti-conformation of N-butane. So we'll go for one by one. What are the conformations possible here? So we'll start from here. The carbon, this front carbon and the back carbon, only two carbon we can visualize. But if you see this one, this C2 and the back side, exactly back of this, there is one carbon, which is C3 carbon. So I will just give the numbering for understanding. One, this one is the 2, and the backside carbon is the third ani, and this backside methyl group is the fourth. These are the 4 carbon for the butane molecule, carbon of the butane molecule. And this conformation is called total eclipsed or eclipse conformation. You can give both. I mean, generally people call it as total eclipse. Sometimes it called as the eclipse conformation. It's also fine. And if you rotate the front carbon atom, we'll keep here the backside carbon atom steady, and we'll move the front carbon atom now. That C1 we move. So if you move this methyl by a 60 degree, we'll get a conformation which is called as the gauge conformation. And if you see this, the first A structure, this methyl group, they are eclipsed to each other. So that's why the potential energy for this one is the 5 kilocalories. And if you rotate the molecule, rotate these carbon bond C2 and C3, the carbon-carbon bond between C2 and C3 is undergoing the rotation here. Just some may in competitive exam people are generally this question came like this, only simple question. They just shown in a, they are just given in the different format. We are not able to understand what they want to ask us. So let me just, here it is. So the question will came like this only. I mean, they just simply ask which bond we gonna rotate, which bond is undergoing rotation in the conformation changes. So the C2 and C3 bond is undergoing the rotation. So from this B structure, so we'll get a structure B by rotating this C2 and C3 bond. And here the methyl group are 60 away from each other by 60 degree. We'll get the conformation called gauge conformation, and the energy for this conformation is 0.9 kilocalories. And similarly, if we try to rotate again by this molecule by 60 degree, so the total angle between the methyl will be get 120 degree. So this is a eclipsed conformation. The first one was total eclipse. This one is the eclipse conformation, in which the hydrogen and the methyl, they are eclipsed to each other. In the total eclipse, the methyl they are eclipsed to each other. If you see the energy difference between this total eclipse and the eclipse conformation, so it has the energy 5 and it has the energy about 3.6. So this 5 minus 3.6, this was the energy difference between the total eclipse and the eclipse conformation. And similarly, if you again rotate the molecule, this methyl group by 60 degree, so the total angle between 120 plus 60 is angle between methyl will be the 180, and we get a conformation which is called anti-conformation, and which is the most stable conformation of the butane. So we call it the anti-conformation. The anti-conformation is the conformation is the bulky group, they are away opposite for each other. Here the methyl groups are away from each other, so it's anti-conformation. And similarly, we'll get the other conformation. You can have a look for this slide. I will upload this one uh, in my drive. All right, so we'll go for the problem based on this. So the preferred staggered conformation for 1,2 dichloroethane. So what is the structure here? So this is structure of ethane, chlorine, 1 chlorine. Here is the one hydrogen. So this is the structure of 1,2 dichloroethane, and preferred staggered conformation. So we'll look for the preferred staggered conformation one by one. So we'll count how many gauge interactions are present between the chlorine and the chlorine atom, right? So these are the chlorine atom. Here, one gauge interaction is present. If you see this one, 1, 2, here one gauge interaction is present, and in between here also one gauge interaction is present. So there are 2 gauge interaction is possible in this structure. If we move for the third structure, here you can see 1, 2. This is one gauge interaction, and this is one gauge interaction present. So here also 2 gauge interaction. And if you look for the oh, this is the structure is correct, incorrect, right? The option D. I'll just rub this. The struct, what is 1, 2 die? 1, 1, 2, sorry, trichloro. The H2 CHCl2, right? This is the structure. So here all 3 chlorine are on the 1 carbon atom, right? So this is the incorrect structure. So this option is almost is incorrect one. So we'll look for this A, B, C, and here you can clearly visualize in the A structure. only one Gauge interaction is present, right? Only one Gauge interaction is present. So that's why the structure A is the triple staggered conformation for 1,1,2 trichloroethane. All right. I'll just come. Sorry for the disturbance. So this is the correct option. Option A is the correct option. Here's some explanation they have given, so you can have a look in the PPT when I upload. The next question is, how many additional gauge interactions are present in cis-decalin and trans-decalin? See, this cis-decalin and trans-decalin. So what is structure of the decalin? Generally we look at. So this is the structure of decalin. And the cis-decalin and trans-decalin. So here you can see this one hydrogen is directed upward. This hydrogen directed downward. If you see the structure, this is the trans-decalin. And if you see this structure, the hydrogen directed upward. This hydrogen also directed upward. So this is cis and this is trans. So that's why it is called as cis-decalin and this is called as trans-decalin, right? And oh, sorry, I have given the answers as well. So the option D is the correct option. You can see here. So understanding main concept is you should know the structure of the cis. Sorry, first the structure of decalin, and you should able to draw the structure as well. So if you can draw one, you always draw while drawing the structure of the decalin. Always draw one cyclohexane in the chair form, and then if you want to draw the trans decalin, so let's say here draw the hydrogens. So this is the hydrogen, this is the hydrogen, and complete the remaining cycle. So here, if you try to complete this remaining, so how it will be? So this is the trans decalin. Because most of the students has the confusion while drawing the decalin system. And from this, if you want to draw the cis decalin, so draw first one hydrogen, draw the second hydrogen, which is cis to each other, and draw a remaining chain or remaining carbon linkage of this another cyclohexane. So here one carbon remaining, so it will directly downward obviously. Here also one remain, which will also be downward, directed downward, and join the remaining carbon. So how it will be? You can draw in this fashion or in this fashion. But if you see this, it directed this side, so direct writing this side carbon is AZ, this side hydrogen is AZ. If you want to complete the remaining cycle. So this is the cis decalin. And the question is, how many additional gauge interaction? Additional they have mentioned. Always read the question carefully. Additional means the interaction present in the trans, they are the number of interaction present in the trans that we need to minus from the total interactions, right? If you see the number of gauge interaction in this one, in the trans decalin system, so how many interactions are there? The 12 gauge interactions are present in the entire molecule. So you have to look for each and every carbon atom. So here also one carbon. So one. So across all these carbon atom, you have to check the all interactions. And in the same in the transdecalin system also, across all this carbon, from here to here, all you need to check one by one. So you will get the idea. But just keep remember these are for the transdecalin. There are 12 Gauch butane interactions are present, and for the cis decalin, 15 Gauch interactions are present. So the answer is 3. 15 minus 12. So you can, instead of drawing each and every structure, always keep in mind how many gauge interactions present in the trans decaling and cis decaling. These numbers you can keep remember, so you can solve the any question. So this is like a memory based question, so you have to remember how many interactions are present in the trans and how many in the cis. So we will get the answer. So the option D is the correct option. The next question is, which of the following molecule predominantly exist in the gauge form at equilibrium? Always remember this at equilibrium, this one is the most important uh, point here. So which of the following molecule predominantly exist in gauge form? So we'll draw the structure of each and every. So if you draw first molecule, the chloro, I will draw on the top and remaining hydrogens. Chloro, hydrogen, hydrogen. So the chloro, they are bulky group. They try to stay away from each other. So the antiform is the major form for this chloro one. If you draw the second structure, third one, and the fourth one I will draw here. The bulky is the group they try. Let's say here iodo, which is more bulky group, so it will always try to stay in the anti-form. It is not getting. It will not try to convert into the gauge. Butane gauge form. Sorry, gauge form. So if you try to draw the structure in the butane gauge form, like iodo, in the place of here or here instead of this. So what will happen? Let's say here and here. So these iodo are the bulky groups. So they repel each other and the compound become very unstable, right? The conformation has the more potential energy. So this is always try to get converted into this form. So this is not always try to convert into anti form. So it will not try to stay in the gauge form at equilibrium. So this is the incorrect option. If you see the bromo version also the same. Bromine are the bulky groups. So they also try to stay in the anti form. So this is also option also incorrect one. And if you look at the fluoro and the chloro, so there is comparison between the fluoro and chloro. And if you see the electronegativity of the chloro as compared to the fluoro, it's lower electronegativity. So it is. If I draw the structure in this fashion, see, if I draw the structure in this fashion here for this molecule, the chloro and fluoro, let's say I will put here X and here hydrogen. The X, the halogen from this one, probably from here or here. Let's say if I draw the structure here for the halogen which containing chloro and fluoro. So this is the bonding orbital, right? The orbital which is for this bonding orbital will be like this. The anti-bonding orbital will be in this fashion. So the bonding orbital contain the electrons or the number of electrons which are present for the bond formation. they are always present in the bonding orbital, and anti-bonding orbital is always vacant orbital. So this is the bonding orbital, and the anti-bonding orbital will be here. So in this molecule, in case of the chloro and the bromo, since because of high electronegativity, this anti-bonding orbital try to take the try to interact with the neighboring atoms to form a favored bonding interaction. So here, in case of the this type of conformation, this anti-bonding orbital and the bonding orbital of this bond, this CH bond, bonding orbital of this CH bond and anti-bonding orbital of CX bond, they are parallel to each other in this in case of the Gauge conformation. So the electron from this bonding orbital and the electron deficient center this anti-bonding orbital, they try to interact in space with each other to stabilize the molecule or to stabilize this bond. So that's why the Gauge conformation in case of the fluoro is more stable. But if you see the chloro, if you apply the same scenario here in case of the chloro doesn't have the sufficient electronegativity to polarize the bond in this format. So that's why just the comparison between chloro and fluoro, the fluoro shows the most such interactions, favored bonding interaction with the antibonding orbital of the CF bond and the bonding orbital of CH bond. So the fluoro, the the molecule containing the fluorine, which shows such strong interaction as compared to the chloro one. So that's why if you see the gauge form of the 1,2-difluoroethane, is gauge form is the most stable form. So that's why this is the B is the correct option. So hope you got the answer for this one, right? So the option B is the correct option here. All right, we got the some more question here. So yeah, here you can see the such how the interaction is present, and you can read the some explanation. The favor hyperconjugation effect. Yeah, you have already probably read the hyperconjugation. So let's say here CH3 and here C, H, H, and H. So for this, let's say here in a X group, so this structure is more stable as compared to so this structure is more stable as compared to this A structure. This is because this structure doesn't have the hyperconjugation effect to stabilize this bond. If the bond try to this X try to pull the electron density from this CX bond, so the hydrogen present in this molecule stabilized by hyperconjugation effect. So that's why such structure are more stable as compared to this kind of structure. And here also the same scenario in this one, this kind of bonding orbital and the antibonding orbital, they are interact with each other and they stabilize the structure, they stabilize the structure in the Gauss form. So this option B is the correct option here. We'll move for the next question. We got one question. Please solve the, what are this option? Question 10. Similar question, question number 10, assignment 4. So I think this is the assignment 4, right? So we have not moved towards up to question number 4. So question number 10, sorry. So this is the question you are talking about. Oh, the assignment 4. Oh, sorry. I think assignment 4 from the current, right? So I will go for that question. I'll open this one. So where is the assignment 4? Can you look once? This is the question you are talking about.
Yes, yes, yes.
No, all right, we'll solve the question. All right, I just pasted here. Sorry, and we'll solve this question directly instead of looking for other options. So what the question is, in the preferred conformation of X, so the molecule, the structure of the X they have given, and both the methyl groups are equatorial, only one methyl group are equatorial, both methyl group are axial. So we'll draw the structure first in the form of chair conformation, and then we'll try to solve which option is the correct option. So if you look at the chair conformation of this molecule, I will draw a simple chair first. So let's say this is the chair conformation, right? And if you look at the, I'll just give the numbering for our understanding: 1, 2, 3, and the 4, right? So I will draw the C4, and here you can see the third butyl group which is directing upward, right? As I have seen, this is the beta, this is upper side, right? So this is the C4 carbon atom, and the third butyl group directing upward. And if you look at the C3, this methyl group directing downward, this methyl group directing downward, and the second one methyl at the C4 also directing downward, right? So this is the structure, and I will just draw the remaining hydrogen atom just for understanding. So this is the structure of this molecule, and if you look at the I'll just for understanding, I will draw the S and R and S configuration for this one also. So 1, 2, 3. This is S configuration for the center. 1, 2, 3. This is N configuration. Right. So we have kept the configuration also the same. Just we have converted the structure into the chair form by keeping the all configuration, absolute configuration of our chiral center same. So this you can directly do the just this methyl is butyl is upward, so you can draw it upward, and this methyl at the C3 and C4 they are downward. So these are the downward directing. So just we have draw the molecule in the chair form, and if you look at the statements, both the methyl groups are equatorial. They have mentioned. So and in the preferred conformation of X. So first of all, we have to look at this preferred conformation of X. So can anyone tell whether I have drawn a correct structure, which is the preferred one, the structure? So if you look at the structure of this one, this conformation is the preferred conformation. Why? This is because this third butyl group is at the equatorial position. So always remember, the most bulky group we have to keep in the equatorial position. The another conformation will be in the conformation. Another conformation will be the methyl group is on the axial position. So that one definitely not a preferred one. So the third butyl group is at equatorial. So equatorial third butyl group is the stable conformation for this one, and remaining group we have drawn as it is. So this is the structure which is the preferred conformation, and the methyl group are at equatorial. Both methyl group are equatorial. Wrong. This is one methyl group which is axial. So statement 1 is the incorrect one. That is option A is neglected. The next option is only one methyl group is equatorial. Yes, correct. This methyl group is only at the equatorial. So the option B is the correct option. And the option C is both methyl group are axial. This is also wrong, because if you see this methyl group is the equatorial, this one is the axial. So the option C is the incorrect. So the option B is the correct option. So clear the doubt? So please let me know if you have, if you need any further.
Actually, while
Uh-huh.
you are converting this chair form, carbon number C4, right?
Right.
Methyl groups adding and X group, I mean X and methyl group adding in fourth position.
Right.
But in cyclohexane, whatever the structure we are observing in question, there you are giving the number one is the first position, right? That is the first in first position. Right?
The numbering you can neglect. Here, right, you can draw any structure, just chair. But only thing is there, let's say if I draw any kind of this kind of chair, right?
But preference will be changed. I mean, preference will be changed, right? That is why I'm asking.
Uh, I'm
Here,
not
bulky
getting
means
the.
dimethyl
Mhm.
attaching. So that is the preference is the first position for that, right? Actually.
Oh, like sorry, why it is not working? So this you're talking about the numbering here. The first one, like this 1, 2,
Yes.
3. Oh,
Yes.
that doesn't matter. I mean, in the final structure, that it doesn't matter. I mean, yeah, if you give the numbering like this way, it doesn't matter. So if let's say if I give the numbering from this one or 2, 3,
Okay.
sorry, 3 and 4. So
Okay.
only thing is,
There
yeah,
is
the
no
numbering
preference.
will, yeah,
Okay. Thank you.
yeah. So in the structure, just for understanding, you can give the A, B, C, D numbering, and then you can draw the structure. Only thing is you have to keep the configuration same, the absolute configuration same. If you see here, I'll just, here it is. Only thing is we have to keep the configuration of this chiral center. Let's say this chiral center, we have to, if you give the numbering 1, 2, and the 3. So the numbering, if you give the numbering 1, 2, 3, 1, 2, 3, this is the S configuration for this chiral center, right? So we have to keep the same here as well. We should not change this numbering. So if you give the numbering here as well, 1, 2, and 3, if you look from the upper side, so this is the S configuration. So we have converted the structure correctly across the center. If you look for the other centers also, let's say if I say look for this center and give the numbering. So the numbering first will be this, second, and this lower is third. So 1, 2, 3. This is R, which changes to S, right? So if you look at the absolute configuration here, so this is the 1, this is 2, and the methyl is 3. So 1, 2, 3, it's R, which changes to S because hydrogen is upside. So we have to keep in mind the
One
numbering. Yeah,
one
the
more thing.
absolute. Mhm.
The both methyls are we are mentioning both are in I mean position is lower side, right? I mean not in
Yeah,
equatorial.
here also you can see the position. It is lower, directing downward, right?
Yeah. Oh, yes, yes. Both are dynamic. But
Yeah,
you are mentioning one is the equatorial, one is the axial, right?
yeah, exactly. Both are alpha, right? Here we can see both are alpha. So in the structure, our structure also, both methyl are alpha to each other. So this is the correct option here. So we'll go for the someone asked on the question 8 from the same assignment. All right, we'll just look for the question 1 as well. Sorry, question 8. What is the question 8? All right, so this is the structure, and I will just take the question there. So see, so this is the structure. I'll just insert one slide. Can someone let me know the audio and the whatever I'm writing on the whiteboard is getting synced to each other,
Yes, we can able.
and the video is on?
Yes, we can able to see.
All right. So I'll just draw the. So the question is the correct order of increasing CO stretching bond following molecule. So the stretching bond frequency, which frequency they are talking about? The CO stretching bond. Correct order of age of stretching. Age of stretching. Okay. How easily we can stretch the CO bond in the following molecule. So they have given the three different structure here, and how easily we can stretch the bond, or we can say, let's say this is the bond, and these are the two different group for this CO, and this is the CO bond, let's say, and how easily we can stretch the bond. It means how easily we can convert this bond to single bond, right? So if you convert the single double bond to the single bond, that will obviously the length of the bond will be increased. So I'll just right. So how easily we can stretch this bond or double bond? We need to weaken the double bond. So when it is possible, when the attaching groups, this A and B, this group are electron donating groups, then and then only this bond, the electron pair of used for the carbon oxygen bond formation, they are more polarized toward the oxygen. Then it can be converted into the a single bond or partial single bond, so the bond length get increases. So we just need to give the write the structure in the form of, in the order of electron electron donating group. And here there is one exception they have given, this cyclopropane. Always consider this cyclopropane is highly electron rich center. This is because it has involved the banana bonds, and which increase the electron in the system. So this structure is very compact, and the electrons are very delocalized in the system of this cyclopropane. So if you look at the electron density here, among this carbon atom is highest among these all three. So obviously the option A is the, sorry, very easily can get converted into the carbon oxygen single bond. This carbon bond easily converted to carbon single bond or partial carbon oxygen single bond. The next one is the, if you need to compare between the tert-butyl and this methyl, this one. So here there is one trick. Here, do you need to consider the inductive effect? Or hyperconjugation? So this is the one challenging situation here. So in these two, which effect is predominant that we have to consider? If you look at the tert-butyl group, which is the kind of more electron rich, we can say, and the methyl group, which is also electron deficient, but it has the hydrogen, which show the hyperconjugation effect. So here, generally, the hyperconjugation effect is the more stronger here. So I just need to confirm whether it is again, but I will suggest for now, I will give the numbering in this way. So as per my understanding, the option B, sorry, which is one, oh, there is no such options. I think this option is the most likely to the correct option here. But there is one challenging factor here. This methyl group can also migrate to this one, and this bond go to the oxygen bond. So yes, this is really challenging question, I think. I mean, there are a lot of factors that we need to consider. I will just insert one slide here and draw here. In case of first option, we need to consider the we need to consider the electron rich nature of this cyclopropane. In the second one, we need to consider the migration of methyl. And in the third one, we need to consider the hyperconjugation. So this one, these are the three different factors, and they are not at all comparable to each other. I mean, we can't give the direct comparison here. So this is, I think, some kind of remembering type question. So I think I will suggest you for this question, you look for some books. I will also look for the correct option, because it looks like the cyclopropane is electron rich, so it has the more ability to form the carbon oxygen single bond by polarizing the carbon oxygen bond like in this fashion.
Ketone, I
Mhm.
think a single ketone is having need more strengthening, right? Actually, compared to
Yeah, the
this.
single ketone obviously has the more strength. I mean, but we have
Uh,
to
no,
solve
it's having
more
it
strength
is
means
not.
less reactive.
Yes,
AZ,
yes, but we can't. I mean,
we need
yeah.
opposite.
See, they are asking. Yeah, yeah. Easy stretching, right? They're asking.
The
So,
option which has the third
single
one,
ketone, I think first one is the right one. I thought. Is it right?
yeah, most likely the first one is the correct option. This is because the hyperconjugation, sorry, highest electron rich nature. This is always try to stay in this form, and also there is one effect called as there are a lot of factors in this system. So 4n plus 2 pi electron, which is aromatic. If you look at this cyclopropane system, double bond O, if it convert into the, sorry, if this cyclopropane convert into in this form, no, there is no double bond, right? So this factor it's not matter here. So, but still there are one factor, which is the electron rich nature of the cyclopropane, which makes the polarization of this bond AZ. And if you, so the A is the one is the most likely to, most easy to stretch the CO bond. And in the second and third, yes, this is the methyl migration is also a predominant effect. We can't neglect that one. And hyperconjugation also the one effect. So I have just confusion between the 2 and 3, but the option, yeah, major will go through the majority. The option A, which contain 1, 2, 3 in the order, which is this option. The option A is the looks like most correct option here. But still, you can should confirm it with the some references. But for now, I will tick for the option A. Does anyone have any suggestion for this? Right, I think option A is the correct option. We'll move for the next question. All right. The next question is identify the conformation. Sorry, I will just keep it on the identify conformation in which the term M gauge conformation can
Hello.
be termed as, yes.
Can I ask actually?
Yes.
Yeah, you were asking. Yeah. In the assignment 4, you're asking the fifth question is there. Which of the following representation mesoform is there, right? Actually, form mesoform.
This one?
Actually, we are observing that. Yeah. Fifth question. Assignment
Oh,
4,
sorry.
fifth question actually.
Oh, the on the regular assignment question. All right, I will go for this.
Yes.
Uh,
Yeah, just I need a small confirmation from there actually.
all right, this is one confirmation. The mesotartaric acid is.
Yes. Here I looks to mean we need to change any. And second is I mean we need to twist and turn it right actually. That is in
Yes.
staggered form. We have eclipse of that is in eclipse form. We need to change the staggered form of that one, right? Second form.
Right. So basically, you can
Yeah,
do one thing
and
simple. For this, I will show the trick. So you directly draw the confirmation. Sorry, you can directly give the numbering and give the RS configuration. So based on that, whichever the similar, whether it is RR or SS, that form is the mesoform.
okay. Thank you.
Yeah, you can give directly the numbering. So in the first case, I will just show
Yeah.
you. Yeah, the 1, 2, 3, it is R, and in the second one, 1, 2, 3, this S changed to R. So the obviously option A is the correct option.
Yes. I keep in
Yeah,
honors one note
yeah, in this
there
way you
because
can just. Mhm.
first one we can able to change to 90 degrees. We can turn to 90 degrees. It may match to that actually. Yeah.
Yeah, right.
Okay. Thank you.
All right. So this one is the. Does anyone have any question? Will so the next question, we'll go for the next question now. If you don't have any question. All right. So the next question is the confirmation in which we can term as a M gauge. So I will just directly go toward the answer instead of drawing all the structure. So, oh, it's not going. Yeah. So these are the structures. So if you see the structure of the molecule, so 1, 2, 3, these are the 4 structures, and in this one, this bromine, they are the gauge to each other. In this one, the front facial, back facial, right? Sorry, front fiducial to back facial. So it's like nomenclature you have already learned in the week 4 videos. By I think in the fourth video, it is professor has explained this one, and in this one there is a front facial and back facial. So it's like,
They need higher energy actually. He has
yeah,
explained methyl, and methyl chlorine something. I think he
right,
explained methyl bromine something.
yeah,
I
which has
think
the highest energy, and
actually methyl having 3.4 something is there, and methyl bromine having
the M,
3
right.
something.
This is the M gauge. This one, this structure. This structure is like a anti-periplanar. This third structure is like a P gauge. We can, and this fourth structure is like a M gauge. So these are the numbering they have given. Like they are a kind of hydrogen, iodo and hydrogen. They are the gauge. So this labeled as the M gauge there. Here it is like chlorine and hydroxy. They are gauge to each other. In this one, this they have labeled at a P gauge, And here you can see the iodo and hydrogen, they are hydroxy anti. So this is anti-periplanar, and this is a little complicated and some kind of informative or mugging type of nomenclature, the terms. So here the option, I will just directly go for these options 1 and 4, where it is. So this option is the correct option. You just look again. I mean, if you have any doubt, you can refer the, I think, video 4, I think 4 or 3. I will directly move for the next question. So where it is. For last question, I have given some explanation here. I have attached some slide, so you can refer that slide for understanding. So the next question is erythro 2,3-dibromobutane. Erythro 2,3-dibromobutane, erythro 3O. So this numbering, can anyone tell which is 3O and which is erythro? So the erythro, which is on this bromine, should be on the same side, and 3O both should be the anti side or opposite side here to each other. And the question is, consider the following erythro and 2,3-dibromobutane. The gauge interaction for MEBr, and that is methyl bromine are 3.3. I'll write here better. 3.3, 0.8, and the BR is 3.0 kilocalories, right? Select the correct order of energy due to gauge butane interaction. So we just need to calculate the energies. So we'll look at the structure and calculate the how many energies for particular molecule is possible. So for the first molecule, we'll look for this one. So this is MEBr. MEBr, how much it is? 0.8. So 0.8 plus, there is one MEBr again. So plus 0.8 other info. So these are the two. So total it is 1.6. So for the second molecule, the BRBR refer 3.0 plus there is one BR methyl. This one BR methyl, right? So BR methyl is 0.8 plus there is one methyl. Here you can see 3.3. Oh, sorry, 3.3. So how much is total? So 3 plus 0.8 plus 3.3.
7.1.
Right. So the 7.1 for the first it is 1.6. All right. And for third, this one is the BRBR, which is 3.0. The BR methyl, it is, how much it is? 0.8. And there is one methyl also here, so which is 3.3. So the total is 7.1. So for A, it is 1.6. For B, it is 7.1. And for C, it is 7.1. So they are equal, and here it is less. So the option which contain 3 and 2 equal, so and 1 has less energy. So the option A is the correct option here. So all right. So anyone have any doubt in this one? How we have calculated? We have just did the summation. So you can just add the how much energy for this molecule. Always try to make in some tabular format, so you will not miss any detail here. So these are the some questions that generally asked in the geoscientist examination as well as the BARC examination. I mean, you should spend less time smartly, because if you see the BARC examination, there are, I think, for one question, there are only the 78 seconds, because there are 100 question and you have got the time about 2 hours, that is 120 minutes. So you have to solve the 100 question in 120 minutes. So you can calculate how many seconds you have for one question. So for such question, if you try to write down very slowly, then you will able to you'll probably miss. So you just need to try to be a smart work instead of writing down entire structure, calculating one by one like this way. All right. So we'll go for the next question if you don't have in doubt. All right. Someone has a doubt in the question 12 in the assignment 4. So we'll go for the assignment 4. Assignment 4 of this current assignment, right? Oh, why it is not working? All right, I will just share the screen. Assignment 4. All right, here it is, the question number 12. What is the question number 12? All right, so they have given I'll just insert the all right, so this is the question. Yeah. The energy dihedral angle curve obtained by the rotating the back carbon by 360 in a clockwise direction, starting from the starting from the conformation as shown. So we just need to draw the energy profile diagram. So this is a very simple question, but only thing is you need to go step by step. All right, so I'll just take the structure of this molecule. So see, this is the structure of the molecule, and we have to rotate the back carbon atom by 360 degree clockwise. All right, so just we need to rotate this carbon atom by 360 step by step, 60 degree each step. And you see the structure, I will just all right, so this is the methyl group. Hydrogen, I will draw a circle just to draw it. I mean, we will not waste much time. So this is the CH3. The front carbon atom is the same in all configuration. We just need to rotate the back carbon atom, because they have asked us to rotate the back carbon atom to up to 360 degree and clockwise direction, starting from the structure they have given. So we have taken the structure as they have given. And if you rotate the structure, the CH3 will be here. Sorry. And hydrogen, sorry. The hydrogen will be the eclipse to other group. So the hydrogen will be here. In the next 360, sorry, next 60 degree, CH3 will be here, and hydrogen will be here. If you further rotate this molecule by this back carbon atom by 60 degree, so the CH3 will be here, and hydrogen will be here. Again, you rotate by 60 degree. This methyl will be here, hydrogen will be here, right? So the round is equal to hydrogen. I will just declare here. So these are the some structure possible, and we have to rotate up to here, right? So two structure are still remaining. So rotate this structure by 60°. How it will be? It will be like CH3 hydrogen from front side, and the back side will be the CH3 just eclipse to this, right? So this is the structure possible. And again, we need to rotate by 360° to get our up to here. So this methyl will go here. So the front methyl will be remain as it is. The back methyl will go here. So here, this structure is the same as the original one. So we got the original structure. So we have rotated this methyl group by up to 60°. And we need to draw the potential energy diagram. So these are the 1, 2, 3, 4, 5, 6, and the seventh one is the same as this one. So I will draw A, B, C, D, E, F, and again A. So obviously the here A, B, C, D, F, sorry, F, and again A. So the A and A are similar. And if you look at the structure A, which has the
పొడిచాడే ముడ్డికి పొడిచాడే నేర్చుకోండి
can you please
కళ్ళు కప్పట్లా బుదురు బుదురు కనపడతాయి నాకు ఎక్సర్సైజ్ చదువు బుక్ ఓపెన్ చేస్తే కళ్ళు కప్పట్లా
I will just remove this person from the meeting. Right. Let it be. So these are the structures possible, and if you can calculate the energies between these all possible structure. So the highest energy structure will be the structure which has the methyl eclipsed with each other. So which is the structure? So this one is the fully eclipsed structure, right? So the F having the highest energy. So the F having the highest energy. So F will be, I will just draw a point here instead of drawing the dark circle. And the lowest energy structure is the structure which has the methyl anti to each other. So the structure C is the lowest energy structure. So the structure C is the lowest energy structure. And other structure will be, we can draw with this. So the A structure which has one butane gauge interaction. So this is the, I will just draw a line so as we can compare the energies. Right. So the butane gauge will has the lower energy as compared to the fully eclipsed conformation, right? So this is the gauge conformation, and in between there will be a conformation which has the partial eclipse. So the A will be here, the B, you can see here there is a gauge interaction, sorry, eclipse interaction between the methyl and hydrogen. So it has some slightly higher energy. The next structure is the anti-conformation, so which has the lowest. So the A, B, C, and for the D, it is again eclipsed. So the D also have the same energy as the B. Here there is a gauge conformation which has the same energy as this one. So here, and again the F which has the highest energy. So this is the fully eclipsed, and again A which has again the gauge. So like this. So the energy curve like in this fashion. So what are the options they have given? So you can see the options. Oh, so we need to take this to that slide. All right. So these are the so this is our potential energy curve, and we'll match with the options. So if you match the match correctly, so here you can see the highest one is the second last, right? Oh, sorry. Wait, so we got the option, all right. So here you can easily compare it with the options given. So the second, this F, you can see here, it is perfectly synchronizing with our curve. And the most lowest is the third one, first, second, third, fourth, fifth, sixth, and seventh, right? These are the gauge, these are the partial eclipsed, and this is the fully eclipsed. So you can see here, in our case, it is perfectly matched. This is the fully eclipsed, these are the partially eclipsed, and this is the gauge conformation, right? And the lowest one is the anti-conformation. So the option A is the correct option here. All right, does anyone have any doubt here now? Can you let me know if anyone have any doubt, so we can move for next question. Question 8 in assignment 4. So this is the, I think, question 8, right? All right, so someone asked the question. So is it clear? All right, we'll move for the next question. The question 8 in the assignment 4. All right, so yeah, we have already solved this one, right? The option A is the correct option here, as per, I mean, our understanding, our discussion. So the option A is the correct option for this one. The seventh question, what is the seventh question? The excess energy that the following conformation has over most stable conformation of N-butane is. So you just need to calculate you just need to convert this conformation in the form of, I'll just insert one slide. You can just convert this conformation in the eclipse and staggered form. So here you can see, I'll just take this carbon as a front carbon atom. So the methyl, it's CH3, and the back carbon, obviously it is methyl and methyl. So this is the structure, and the excess energy that the following conformation has over most conformation of N-butane is 1 gauge butane interaction butane energy is 0.96. Oh, just need to calculate the energies here. So you can just calculate the energy. You can calculate for this one. You can see one gauge interaction here, and this is one gauge. This is second. This is third. This is fourth. This is fifth, and this is sixth. So 6 multiplied with 0.9. So how about 5.4? The excess energy that the following conformation has over most stable conformation of N-butane is. So this is the total energy of this conformation, and most stable conformation of N-butane is, so N-butane, so this CH3 and this CH3, which is anti to each other, which is the most stable conformation of N-butane, and how much energy it has. So you need to calculate the energy for this stage. It has almost zero, gauge interaction, right? There is no any gauge interaction. So the 5.4 is the correct option here. All right. Does anyone have the doubt in this question? So this kind of questions you can solve here. The sixth question. So these are the very simple questions. You just the number of gauge interaction in the most stable conformation of 2,2,3 trimethyl butane is. So you just draw the structure and calculate the number of gauge interaction for each, and which the conformation which has the lowest gauge interaction, that is the stable conformation. All right, so I'll just number of gauge interaction. Number of butane gauge interaction for most stable conformation of 2,2,3 trimethyl butane. I will draw the structure first. So this is the butane and 2,2. So this is 1, this is 2, 3, and 4. So the 2,2 dimethyl. So here is one methyl, here is one methyl, right? And another is the at 3 position also there is one methyl. So basically there are 2 methyl for the front carbon atom. So if you draw the front carbon atom, there is 3 methyl. So we are looking for this C2 and C3, right? C2 and C3. So this is the C2 and this is front carbon atom. The backside carbon atom will be the C3, and which, as you can see here, there are 2 methyls. So obviously one methyl here, one methyl here. So what is the possible structure? So here you can see the front side is almost symmetrical because it has already 3 methyl groups. So it is almost symmetrical right here. So you can compare, there is no other possible structure for this molecule. This is because if you rotate the molecule by 60°, it forms the eclipse conformation. So that will be obviously the unstable one. And we need to find out the butane gauge conformation. So the gauge conformation is this hydrogen need to be here or here. So if you move the hydrogen also, then the interaction will not going to change. So the number of gauge interaction possible for this molecule, that we need to calculate. So how many gauge interaction for this molecule are possible now? So I'll just rub all this stuff. I will draw. So this is the front methyl groups. They are symmetrical, so there is no meaning to rotate the molecule from the back side. So here there is one interaction, here second, here third, here fourth. So the total 4 interactions possible for this molecule. So in this way you can solve any question. Just we need to draw the structure, convert it into the Newman projection formula, and you can just count number of gauge interaction, stability of the different conformations and all. So we will not solve entire assignment here. We generally, yes, please.
Whatever the sixth question, that is they are asking about the stable conformation, right?
This same question, right? The number of gauge butane interaction in the most stable conformation, right?
Right. Yes.
So
Yes. While doing stable conformation, I think it's coming 3 only, right? Just check it once again now. Please look it on.
So see, this is the structure, right? For the
Yes.
molecule. So which conformation is the most stable? So if you try to draw the different conformations from this molecule, so what are the possibility here? The possibility is the methyl, because see on the front carbon atom there are 3 methyl present. So if you rotate the backside carbon atom, the number of gauge interaction will not gonna change. We'll try for one. So if I rotate this hydrogen in the place of here, so hydrogen will be here, this methyl will be here, and this methyl will be here. So in this one also you can see there is 1, 2, 3, 4. 4 gauge interactions are possible. If I rotate this hydrogen by in this anti-clockwise direction, then which structure is possible? The structure which has the 3-methyl group already here, and hydrogen now I have rotate to here, right? By anti-clockwise. Here I have rotated clockwise, here I have rotated anti-clockwise. And the methyl will be grow to different position too. Now we can calculate here. 1 interaction, 2 interaction, here 3 interaction, and 4 interaction. So there are 4 interactions possible. Because you can see here, the front methyl group or front carbon atom is symmetrical. So if you rotate any way back carbon atom, the interactions will not gonna change, right? So that's why the 4. So these are the 3 structures are possible, and all the 3 structure has the 4 gauge interaction. So these are the 4 structure possible, and all 4 has the and if you look at the structures of these are 3 structure possible and 4 gauge interactions in each structure. So all structure are almost identical because the front carbon atom is the same. With carbon atom which has the 3 equal groups. We can see the methyl. Because 2 dimethyl. So numbering 1, 2, 3, 4, and 2, 2, 1, 2. Sorry, 2. Sorry, these are 2 methyl groups for this carbon atom, and one already in the chain. From the butane chain. So these 2 methyl for the C3 carbon and 1, 2, 3 methyl from the C2 carbon. So this C2 carbon has the 3 identical group. That's why all 3 structure has the equal interaction, equal possible gauge interactions. So this is the only the 4 these are 4 3 options, 3 possible structures, and all 3 structures has the 4 gauge interactions. All right. So we should not solve all assignment questions here, but we'll just I will just discuss the question 9 in the 4 assignment. What's the question 9? So see, so they have given total number of isomers, both stereo and constitutional isomer, that are obtained by the photochemical monobromination of but1 in N-bromosuccinamide. So draw the structure of this but1 in but1 in, and reaction of the but1 in with the N-bromosuccinamide. So that reaction you have to perform, and the product, what are the products possible that you need to draw. And if you draw the products, then you have to consider the stereochemistry as well. So you need to convert that products into the different products by drawing their possible stereochemical products, right? So you can draw the structure and perform the reaction. I will just show you the how to solve this one. I will not entirely solve the question because this is from the current assignment. So let's say such type of question they have given. I will take the one. So this is the but1 in, right? And NBS. If you do the bromination with the NBS, so how the bromination will work? So it gives the bromo product, right? So these are the 2 isomers possible. Now, for this, is there any stereochemical possible structures? No. So for this is the only one stereoisomer for this product also. And if you see this one, it has the chiral center. So for this, there are again 2, right? So 1, 2, and this is the 3. Like this, we can do any reaction on any molecule, and you just need to convert the starting to product. First, always try to convert into the starting to product. Don't look at the stereochemistry first stage at first glance. So you convert into product, and if there are number of products are possible, you can draw that product, and now independently look at each product whether there is stereoisomers are possible or not. So first constitutional product you have to solve, you have to check, and then stereochemical. So this is the this kind of questions you can generally saw in many examination. You can solve this question in this way. All right, we have covered most of the questions from the week 4 assignments as well. So if you don't have any doubt, so you can ask any generalized question. I'll just stop the recording and where it is.